Okay, so we're switching back to random graphs, maybe slightly related to this late morning talk, and Samuel will take over. Board talk, right?
Yes,
Excellent.
I think so. Thank you for the introduction, and thanks for the invitation to this very nice workshop. So today I want to speak about joint works, especially 4 collaborators. And I want to emphasize that it started with Nicolas Keriven, let's say around 2019. And then we worked with Alberto Bietti, who is currently at Flatiron, Mathieu Cordonnier, who was a PhD student with Nicolas Keriven, and also Nicolas Tremblay. So the story started outside the machine learning community. We were trying, if I remember correctly, with Nicolas Keriven, to understand the paper by Ulrike van Doxburg, consistency of spectral clustering. And this, let's say, this paper is quite heavy on the functional analysis side. And we discovered that later on, was this very nice paper by Ley and Rinaldo in Analostat in 2013. We were describing what happens for spectral clustering when your graph grows large, okay, under the stochastic block model, okay. And we worked a lot around this paper, okay, for different reasons. But at the start, it was linked to dynamical stochastic block model. But Nicolas had this very nice idea to use one of the results to analyze graph neural networks. Okay. So a lot of what I will present today makes an echo to what Luana presented during the bootcamp. But it's not directly related to Graphon, and I will explain why in a moment. Okay. So it's very close, but still quite different. So what's the main idea that we wanted to tackle? You have a graph, G, okay, in the space of graph, whatever it means. And you take another one here, okay, and you make a graph neural network act on this graph, okay? So for the moment, let's use this notation, okay? And you want to compare somehow the difference between these two outputs, okay? Depending on the difference between these two graphs. So as a lot of you know, it's the question of putting a metric on the space of graph is a really difficult question. And so the idea here was to say, okay, let's make a connection here to a different space. Oops. A space which is a metric space, okay? And here, hopefully, we will be able to say more about it, okay? So the idea is to, I will discuss 2 main things, okay? Is to say how I can construct an object that is nicer, okay, where the metric is nice, and how you can afterwards relate this to the difference between these two graphs.
And this mapping is what?
So here the mapping from here to here will be 1-to-1, yes. Okay. So the trick is the following, is to use what can you call latent space model, random geometric graph. So here geometric, yesterday in the talk of Anna, geometric meant R3. Here it's more like something where you have a nice geometry, okay? It's slightly more general. And a latent space model will be given by a probability measure on some space, okay? a connectivity kernel, W, and eventually some function. I will discuss about this point in a moment. Okay? When you have this, okay, what you will do is that you draw in a high ID fashion points according to this probability measure, okay, on some metric space. Let's say to simplify the discussion that this is a compact subspace of RD, but you can be slightly more general. Then you will draw a graph according to the adjacency matrix. And how you will do that? You will take a Bernoulli, AHG, as a Bernoulli law according to the connectivity kernel, okay? And the important fact that make the difference with the graph model is that here you will have a sparsity factor, alpha n, which will allow you to somehow take into account the number of nodes when you draw your points. And you have optionally some node features which are just the action of f on your latent variables. Okay? So the first thing that I want to put an emphasis is that in practice, okay, xi here is unknown. Okay? This is why we say it's a latent position model. You have never accessed directly to the metric space. What you have is the graph. Okay? But you know that it came from some random model. So a comment about alpha n, the sparsity factor. So if this quantity is proportional to 1, what you get is, provided that you take the connectivity kernel on the 0-1 interval, you get exactly the Graffon regime, or in other community, the dense regime. Okay? It means that you will play with graphs that are dense. Okay? In average, you have n square neighbors. On the other part of the spectrum, you have the regime where this sparsity factor is proportional to 1 over n. Okay? This is the sparse regime. So the sparse regime in the random graph community is known to have mostly conjecture. Okay? So it's heavily driven by the statistical physics community. They use a lot things like the replica method to have strong conjecture and formula in this regime. Okay? But from a mathematical point of view, it contains essentially only very hard questions, okay? Except some specific points that you can address. And thanks to the papers that I was discussing, so this Ley and Rinaldo paper, there is a regime alpha n proportional of log n over n. So which I will call the relatively sparse regime. So in practice, obviously the log n, you never, yeah.
So if I compare this to standard Erdős-Renyi graphs with these edge probabilities, so I could take, Erdős-Renyi random graphs where I just flip a coin, and there's a growth rate. It could be 1 over n. It could be log n over n.
It depends how you put the dependency, but typically it's in the.
Are these a special case of this?
It's in the dense regime. Yeah. So I will give you some example of, but yeah. Thanks for the question. Let me answer it in just a second. So. Okay, any question on this regime? Okay, so you can guess that the log n over n in practice behaves like 1 over n. Okay, the log n, you need to have very, very, very large n to make a significant difference between the two. Okay, so example. So the first one is the Herder-Shreni model. So in this case, you can take your metric space to be whatever. Okay, but yeah, really whatever. And the important thing is that W is a constant. Okay, so you have something which is constant, and you will draw according to a probability P each of your nodes. Maybe a slightly more interesting example is the stochastic block model. Okay, and in this case, so there is different way to cast it as a random geometric graph, but you can say that you have only a finite number of points. Okay, big N, Y, and then W is a piecewise constant matrix. Matrix. You have epsilon graph. So epsilon graph means essentially that the connectivity kernel between 2 points is just the indicator function of the distance between your points. Okay? So you can think of, you have a lot of points and you are connected if you are in the metric space at distance at most epsilon. And another thing that when you have kernel, so for instance, the Gaussian kernel. And let me give you a complete example. So for instance, you can take X, the probability measure, to be a Gaussian, a mixture of Gaussian. Okay. You take your connectivity kernel to be 1 over some constant exponential like that. Okay. And you can, for instance, add some features. So I don't know, you can put the norm of them. Okay. So, and essentially, in this kind of model, when alpha n grows, okay, your graph tends to be denser and denser. Okay. So, in terms of, I put assumption on this model for the remaining of the talk. So I will give you some informal statements mostly, but I still want to give you, let's say, some idea of what kind of hypothesis we need. So we need to have an upper bounded kernel. I think we really don't know how to work without this assumption. So it means that for all x, the norm of the absolute value, sorry, of this map is smaller than some constant. You need to have a lower bounded degree. So it means that for all x, the degree function will be bounded. So the degree function is the integral over your space according to the measure. So this thing should be bigger than C mean. And we will also need to have Lipschitz, piecewise Lipschitz kernel. So piecewise Lipschitz means there exists a finite partition of the space on the interior of each piece. You are Lipschitz. Piecewise Lipschitz kernel. Okay. Okay. Any question on this model?
Sorry, why are we trying to define these latent space models?
Sorry?
Why are we trying to define these
Why?
Yeah.
So why? It's because it will help us to define this object in a moment.
So you're trying to define a metric?
Yeah. So as you can maybe guess, here, so this thing will be a metric space where you have a natural metric, the Euclidean, for instance. Okay? And I will use it in a moment to tell you how to measure this difference and to go back to the space of graph. So this is, let's say, the mathematical part is fun, but this is really to have the tools, a metric tool that is easier to manipulate than other. Yeah.
Basically, we're just reflecting into another space and molding it into a geometry where it makes sense for both.
Exactly.
Right. Even if the graphs don't really align with one
Exactly.
another, we're just going into a space
So
that can fully represent it as much as possible.
Exactly. Let me go a lot into the talk, but this is exactly that. I want to have some way to have a good notion of metric, in the sense that you all know that the graph isomorphism problem is difficult, okay? And I want a way to, let's say, go outside this question and completely forgot the isomorphism problem. This is one way. Yeah.
How is the number of nodes and so is it fixed or we also?
It will grow. That's
Sorry?
the number of nodes will grow. That's why you have this sparsity factor with the small n. So this is the remaining of the talk will be what happens when the number of nodes grows to plus infinity. Wait a moment, it's in 10 minutes.
Is this also, I'm trying to understand what's the difference between this model and the spatial inhomogeneous random graph? Because I think those are
There is none, I think.
inhomogeneous random graphs that are spatial. Yeah.
Yeah, I think that's, I mean, so I'm not exactly sure the kind of assumption that you put with the homogeneous one, but that's the same.
One more thing. Basically, you're trying to define a function that can predict the evolution of a graph over time, of how it changes.
So here for the moment there is no time. Yeah, you can
Like how
you can look at n as the time, but that's not really the point of view that I will take here. Yeah.
Have you considered Banach spaces where those two assumptions can be removed, right? The first.
Here?
Yeah.
So you mean instead of compact metric space to put a Banach space?
Yes.
So the kind of tool that we use and that I will not develop a lot don't really benefit from the Banach assumption, because so at the end the machinery behind it is concentration result,
Okay.
and I'm not sure that I will gain something by adding the Banach assumption, but maybe.
Yeah.
We are user of concentration results, so maybe it's possible that that's something.
Thank you.
Okay, so I will, like everyone, now introduce you what is a graph neural network, of course. But I will give you my notation. Up. So in general, I will be in the, let's say, in the context of message passing GNN, okay? So nothing more general than that. And in fact, it was the work of our PhD student, Mathieu Cordonnier. But I will mainly talk about a spectral, so more or less a spectral version of it. So let me be slightly more precise. So if I write down what I mean here by message passing, I mean that each layer, okay, is some aggregation function, okay, of what happens locally at the previous layer and what happened for every neighbors of my node. Okay, So this is more or less the same thing that we saw since the first talk yesterday. Okay, and one way to cast this kind of function, okay, so one choice, is to define it in a recursive way thanks to a shift matrix. So when I say shift matrix, I mean adjacency matrix, Laplacian matrix, normalized Laplacian, and so on. Okay, so one choice is to use a shift matrix. Let's call it S. Okay, and this way I can write it in a concatenated way as big Z or L of 1 is some nonlinearity applied to what happens at the previous layer, okay? Like, let's say, the MLP part somehow, okay? Plus what happened thanks to this shift matrix, so think of the adjacency or the normalized, okay, with some other weight, and eventually some bias that you can add, okay? So here you have a nonlinearity. So to be specific, I need it to be one Lipschitz. So things relu, for instance. Here, so all ZL are the node embeddings. Okay, so these things live in Rn times dl, or dl is the dimension of the embeddings at node L. These two things are the learnable weights. And this is the time to tell you that I will absolutely don't discuss the training procedure. So everything is already trained. Okay, you have an oracle giving it to you. And this thing, as I told you, was the bias. Okay. And so essentially, when you do graph machine learning, you are either doing stuff at the node level or at the graph level. Okay? If you are at the node level, you will require to have something which is a permutation equivariant. If you are at the graph level, you will ask something to be permutation invariant. Okay? So to simplify the presentation, I will discuss only the equivariant case. But in the paper, we also did everything for the invariant. So I will ask permutation equivariance. So the last layer, okay, so my neural networks with weights theta associated to my shift matrix S with initial nodes embedding Z0 will be the last layer, okay, plus potentially some bias. Don't know why I kept the bias, because, okay, and you can replace these linear things by MLP if you prefer. It doesn't really change a lot. What is important is that you need something which preserves equivariance. Okay, and as I told you, nothing is really more difficult if you put a mean or an average at the end of the computation. Okay, so any question of this model of MP-GNN? It's probably the less complicated that we saw up to.
Understand it correctly, you're taking one is globally and you're attaching a weight of how it changes, and then one at the node level and attaching a weight to it.
Yeah.
And then adding a bias, right?
Yeah,
and
exactly.
They're just trainable, so you have a global and a local.
Exactly.
Okay.
Okay, so the 3 points that I want to address, and I will not address the 3 of them, are the following. So the remaining of the talk is, first, question 1. What happened in terms of convergence of this GNN when n goes to plus infinity? So this is this part. Okay. Question 2. Can I say something? So let me spoil you spoil you, I will define something which is called continuous GNN. Can I say something here? Okay, and when I have the difference, when I have these two ingredients, okay, I will just plug the triangle inequality to conclude. And if I have time, I will discuss also some recent universality result of CGNN and the link with positional encoding.
So, sorry.
Yeah.
You said this is node level? Or
Yeah.
graph level?
Node level. Yeah, because I don't put, I mean, I will not average what happens at each node. I just put them this way. So I may be doing node classification, node regression, whatever. Okay, so convergence of GNN. So under suitable assumption, so for instance, it's true for the stochastic block model, thanks to Lai and Rinaldo. What you have is that the discrete shift matrix S, which is an object from R to N, from N to N. And you will see that informally I use S, but here it's S, this N. But I won't keep all the N in the talk, otherwise we are going to go crazy. Okay? Has some limits, okay, when N goes to plus infinity. So let's call it $, okay, which will be an object in L2 of the probability measure that we don't have anymore. That was the probability measure on your metric space. Okay? So you have to trust me, okay, that for instance, for stochastic block model, for the epsilon graph model, okay, typically you have shift matrix that admits a limit, in some sense, we will come back to it, okay, towards an operator, this time, in L2 of P. Okay? So I just want to say here, so S, this shift matrix, act on somehow embedding, okay? Here you have this, okay? So you have this shift matrix. It takes some, let's say, when I say embeddings, you can say also in the signal processing fashion, a graph signal, okay? Here, this operator, $, okay, act on the function on your latent space, okay? So this thing, S bar, is something which eats a function which turn out to be a function defined on the space X. Okay, so remember that we had this definition of a graph neural network, okay? Based on some ingredients, a nonlinearity, learnable parameters, okay, and some bias. And what you can say is that when you do this recursion here, what you do is that you propagate the signals over the node thanks to this equation. And you can define another object formally for the moment. Up. So for any L2 operator, sorry, when I say L2P, here it's the action of $, on P. It's an operator over L2. So we can define continuous graph neural network. So CGNNs. Okay, and what it will be you take this equation and you formally replace the action of the shift by the action of the operator $, here. Okay? So it means that given a function f of L in L2P. Okay? Then what you will have is that the next layer will be the same nonlinearity applied pointwise. Okay? And this is the important part here. You will use the same dimension of the learnable parameter, okay, acting this time on a function, okay, plus same thing here of your dollar operator on the previous, and eventually some bias. Okay, and the important part is that this thing is itself an element of L2P. And the output of your graph neural network, this time, so I will overload the notation of dollar and some initial function, is just the linear combination like before, plus some bias. And here what you do is that you propagate function, okay, over your latent space X. So something which is remarkable in this construction, I think, is that here the learnable weights are the same. Okay, they live, so an oracle, a training procedure gives them to you, and you can look at these two objects from these parameters. Okay, so they are finite dimension, you can train them, and somehow you can, conceptually, you can always look at this just as a continuous version of the previous one, but not with continuous parameter here. Okay? This is exactly the same that you use on the two sides. Is there a question at this point? No? Yeah.
How are you getting the function?
The function?
Yeah.
So for the moment, I'm just starting, like any induction, I'm starting from whatever the function you want. And I will give you in a moment the link between F0 and Z0. Z0 will be just a sampling of your function. Just a sec.
Okay. You'll show us how to map it.
Yeah.
Okay.
Other question? Okay. So to answer the link, so the question for how you can go back and forth between the discrete world and the continuous one, we are going to just establish a sampling lemma. So very basic one. So I'm going to use the MSE norm in the sense that when I have a matrix A square MSE is just 1 over n, okay, of the Frobenius squared norm. Okay, so the sum, the square root of the sum of the square of every element.
Sorry, what's n?
N.
It's n?
Yeah, is that the same n? It's just that.
What is n?
Okay. Ah. You remember this thing in blue here? In blue. Sn. It's if you have a sequence an, okay, of matrix, I will just rescale everything by 1 over n. So you always need to rescale by 1 over n.
That's n as a Nancy, not n as a Mary, right?
Sorry?
That's n as a Nancy, not n as a Mary, right?
MSE as?
It's n as a Nancy, as a no, right?
It's
Or
an
is it-
N.
Ah, yes. N. Yeah. Yeah, thanks.
That threw me off a little bit.
Okay, and so my sampling operator will be the following function. So given some points xi living in X, okay, I will say that I sample, so here, this is a metric space, here it's a set of points. I will sample according to this random variable x, my function, to be just f of xi. Okay, so this is, you take this operator and it gives you the evaluation of your function at some point. Okay, and this thing is to be understood again, n can grow to plus infinity. That's why I don't put n everywhere, otherwise you will be n underscore n and n n. Okay, everything depends on n here. And so a simple lemma is the following, is that if x is compact, but we already said that it is, that the spectral norm of your shift operator is bounded. That might be restrictive, but so in particular, you cannot play with the adjacency matrix. You need to rescale the adjacency matrix by some factor. Otherwise, it's not true that the sequence is bounded with respect to n. And that for every function in L2P, you have that somehow the difference between your shift operator applied to the sampling operator of your function minus the sampling of the shift operator here, f, in MSE goes to 0 in probability, okay? Then you can conclude that any equivariant MP-GNN that we defined previously, according to some nodes, will have the following property, that you take your shift matrix, the sampling of your function, initial function, okay, minus your, this time, your continuous GNN according to the shift operator, but this time with F0. So this difference in MSE goes to 0. So what I'm saying here is that if my shift operator has some nice property that I can prove, for instance, for SBM, okay, being that you can somehow commute the shift and the sampling up to some error that goes to 0, then you can say exactly the same thing for your MP-GNN. Okay? It's not that hard, but it's not that trivial either. Okay. So let me be slightly more precise to state our main result in terms of convergence. What is the dollar operator? Okay, because it's not, I mean, some abstract object. You can clearly define them. So convergence of GNNs towards C GNNs. So for instance, if you take A to be the adjacency matrix, okay, and you recall that alpha n is a sparsity factor, okay, you can define the normalized adjacency matrix, okay, and this thing will have the good idea, for instance, for again SBM, to converge to this operator, which is just the integral of your kernel according to this function. Okay, so does this formula make, before I give you the other example, which is the Laplacian, does it make sense for you? It really means that here, okay, I will integrate to have the shifted version of my function at the point x. I will just integrate my function, okay, but according to the connectivity kernel, okay? So if you think of something, for instance, a Gaussian kernel, I'm just saying that I average my function according to this kernel, okay? Right? Another example is that if I take S to be the Laplacian matrix, the normalized Laplacian matrix. It's minus me. I can show that this thing will converge to a normalized like Laplacian, meaning that I will take my connectivity kernel divided by there might be a square root, sorry, here. But essentially, what you get is another way, okay, to average your function around it. And this thing is a degree function that we define at the beginning as the integral of your kernel along the direction x. Okay? So our main result in this context is the following. So if for any rho, for any probability rho positive, okay, if n is bigger than 1 over rho, okay, and alpha n is bigger up to a multiplicative constant log n over n, so it means that you are in the relatively sparse regime, then with probability 1 minus rho, sorry, you have the fact that this difference, okay, so here x have 0 minus the continuous GNN will be in MSE. So this time you don't just get that it goes to 0, but that it is smaller up to multiplicative constants to the dimension divided by square root of n plus 1 over square root n alpha n. So let me just comment a moment about that. So this thing here, this is just a chaining argument if you are familiar with it. Okay, so this is the reason that I ask X to be a compact space is to be able to do chaining arguments. Okay, and chaining, sorry. And this thing use, let's say, the mechanism of Ley-Rinaldo's strategy to have good concentration of the shift operator. Okay, so this is Ley-Rinaldo for let's say the Laplacian case, and we also work with Nicolas to have slightly more general and more precise concentration. But the main idea was in this paper of Ley-Rinaldo. Okay. Any question to this point? Yeah.
Just wondering whether you said compactness.
Yeah.
Don't you study it on the topic of topological spaces? You can have those properties as well and consider these GNNs as genuses in the topological space.
So I understand your question,
yeah,
but I have absolutely no idea on the tool to use. I'm not familiar enough.
Van
with
Kampen's theorem and all those can be used for isomorphism proving.
I'm pretty sure that you can have before going that abstract,
right.
I think that, I was talking with someone about that. Probably the main thing is to remove the compactness assumption to work in hyperbolic space or things like that. Okay, but I don't master the tool behind it to tell you how the proof will carry on in this case. But probably you can do extension.
Thank you.
Okay, so yeah.
So how does this result compare with the transferability results that one presented?
Okay, so if I'm not mistaken, okay, Luana's and yours result is mainly in the Graphon regime. So for dense graph, and I think that the specificity of this strategy is to be able to deal with in the relatively sparse regime. If the only thing that you consider is dense graph, I would say that the Graphon strategy is way more elegant. I mean, Lovas did it for a reason. It's that this is probably the correct way to look at the convergence of a dense graph. But for relatively sparse graph, you unfortunately don't have anything in terms of cut norm. So I would say that this is a more naive way, and at the same time, slightly more general in terms of graphs that you can handle. So that's, I don't know if I perfectly answer the question, but yeah.
Shouldn't alpha n being smaller than log n refer to sparse graphs?
For sparse graph,
Yeah.
I don't know.
Ah, okay.
And I probably will not, I guess I will not know before my death. I mean, the question that you have behind is too difficult, I think, to be handled, except in very specific case. Okay, so I think it was 45 minutes to talk. So I can either stop at this
So you
point, that
also
was
have
part
15
one.
minutes of questions, so you can also go to your question time
Okay.
if you like.
Yeah, I think I took a lot of questions, so maybe I can continue a bit on the stability and. Okay, so point 2 is now that I have a way to say how this quantity behave, so with this rate, what can I say about this? Okay, that the objective is to have the two lines. So let's discuss about the stability of continuous GNN. To stability of CGNNs. Okay, so since the time is running short, I will not do a very deep review of what is the stability of classical neural networks, but just let me see that if you speak about classical in the sense not graph related neural networks, okay, then essentially at the first order approximation, you have two strong results, I would say, is that the one is for the scattering transform, so by Mala and co-author, okay, and also for convolutional kernel network, by Bietti and co-author. Okay, so the same, obviously the same Bietti than the one we worked for this thing. So, what you get for these two kinds of neural networks is that if you have a C1 diffeomorphism, okay, no, diffeo. Okay, so if tau is a diffeo, then if you make act identity minus this diffeo, what you can say is that typically you can measure the difference between your neural network applied to some function. Okay, so let's play only in the continuous world, minus phi f composed by identity minus this perturbation, and what you get is something which will be controlled somehow by the gradient in infinity norm of your perturbation. Okay? So in submetric space, you need to put a lot of assumption. And the question is, how can I have something similar for graph neural networks? Okay? So let me just say that for GNN, there is this nice paper by Gamma and co-author in signal processing, I think, yeah. That tell you that for some kind of GNN, you have a control, okay, that looks with some distance, okay, around your graph, in the graph world, but this distance is hard to manipulate. It's not the cut metric, it's not LP metric, okay? This is something a bit complicated to state, okay? And our work is to say, our goal was to say, can we have something that tell you when your random graph model is deformed, can I have something that look like that, but for continuous graph neural networks? Okay? And the result that we obtain, stability, sorry, yeah, here was the following. That remember that the latent space model, let me rewrite it, is something which is defined over a metric space. Okay? So in particular, you have a metric. Okay? So remember, you had gamma, it was x, no, p, sorry, w, f, okay? And so this thing is defined on X compact metric space. Okay? And so the result that we have is that it's quite informal, but for translation invariant kernel, you can say stuff when it's not translation invariant, but it's way more difficult. If you replace W, so W is a connectivity kernel, by the deformed version, so remember that tau is a C1 diffeomorphism. So if you replace the connectivity kernel by the translation by this deformation, Tx prime, okay? Or, and, it depends, you replace the probability measure by the push forward of the diffeo toward this probability measure, or that you replace the not features, okay, by the composition of this deformation, then the deviation between, so let me write it like that, the deviation of the CGNN is controlled by the infinity norm of the gradient of the perturbation. So it means, just to put it in equation, it means that you look at S here. So let me write it like that. S F0 minus phi S dollar, sorry. F0 here, and here you add W P F, and here you have W tau, P tau, F tau. This thing is controlled by the norm of the perturbation. Okay? Times F0. Okay, so I think I will stop here and take your question, and I will skip the universality part and positional encoding. Thank you.
There were already a lot of...
Yeah, I have a lot of questions, so I think we can...
Okay, cool. So I want to thank Sam again.
Thank you.